Hello everyone, welcome back to Spectrum classes. This is my fifth video on the topic phase rule, and in this video we are going to discuss the derivation of phase rule. How we are going to derive this Gibbs phase rule and what are the important points which needs to be considered here. And in my previous video I have already discussed about the number of phases, number of components and degree of freedom for a given system in the phase rule, and how we are going to determine them. So if you have not checked my previous videos, please go and check them first, and then you will be able to understand the concept here in a better manner. So let's start with the video. Derivation of phase rule. So first consider a heterogeneous system having p phases and c components. As I discussed earlier, this phase rule is applicable to the heterogeneous system. What is called heterogeneous system, that I have already discussed in the first video on the topic phase rule. And this heterogeneous system is having p phases and c components. Now coming to the number of variables, and these number of variables are also known as degree of freedoms. The degree of freedom of a system is defined as the number of independent variables such as temperature, pressure and concentration or composition, which must be specified in order to define the system complete. So here, what is the relationship between the number of variables, number of phases, number of components is derived in this phase rule. So number of variables is equal to total number of independent variables minus number of relations between these variables at equilibrium. So here it is important to determine the number of variables. We must understand total number of independent variables and the relationships existing between those variables. Since each relation diminishes the number of independent variables by 1. So that is why it is important to know the number of relations between variable equilibrium condition. So first we are going to discuss the total number of independent variables. Total number of independent variables equal to temperature plus pressure plus concentration variables for p phases. As I mentioned here, we are having p phases for the heterogeneous system and c is the components. First, we are going to discuss the temperature. At equilibrium, suppose we are having two phases in equilibrium. This is alpha phase and this is beta phase. And these two are having temperature as T alpha and beta phase has temperature T beta. So in equilibrium, it is considered that the temperature of each phase remains same. So it is defined here at equilibrium, temperature of every phase is same. So there is only one temperature variable for the entire system. So it is 1. Numeric value equal to 1 temperature. Now coming to the second term, pressure. So it is again considered that at equilibrium each phase has the same pressure, so there is only one pressure variable for the entire system. So again we are having one numeric value for the pressure. So 1 plus 1, 2. Now coming to the concentration variables for P phases. Here we are having two phases, two concentrations. So concentration of, this is one component, component 1. Don't get confused with the concentration term and component. So component 1 is in equilibrium with the component 1 in the beta phase. Component 2 is in equilibrium with the component 2 in beta phase, right? So concentration variables for P phases we are going to calculate from this relation. If we are just considering the component 1, then in number of phases, this one component will gives us 1 into P concentration variables, one component P phases. If we are having two components and P phases, then it will be equal to 2 into P concentration variable. If we are having suppose C components, C1, C2 dash 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 and C components in total. Then how many concentration variables will be there? Number of components into number of phases. These are the concentration variables, right? Coming to this total number of independent variable can be written like temperature plus pressure plus these are the concentration variables. Here you please do not get confused with this P and P. Here I italicize this just to differentiate between these two. This is for the pressure and this is for the phases, right? So this equation can be modified as 1 plus 1 plus concentration variables, that is Cp, right? Now coming to the number of variables. So number of variables is equal to total number of variables which we have evaluated here minus number of relations between the variables at equilibrium. So here, since concentration of the components is dependent on the relations exist there, so it can be evaluated with the implied restrictions. So guys, you please do not get confused here. We need to evaluate or subtract the number of relations which are existing between the variables at equilibrium. Since here each relation diminishes the number of independent variables by 1. So these are the number of independent variables. So this quantity will be changed on implying the number of restrictions. So these concentration variables have different relations. So I'm just giving you here a brief overview which kind of relations it will. So suppose this is the diagram for different phases having number of components C1 to Cc. So these components related to each other by their mole fractions, and the second type of relation is they are related with chemical potential. So we are going to discuss the number of two different type of relations which are existing for these concentration variables, right? So first we are going to discuss the relation of these components with their mole fractions, and thereafter we are going to discuss the components in different phases related with their chemical potential. So we have to first evaluate those relations, and then after only we will be able to determine the number of variables. So I am just going to elaborate this term. Suppose the concentration of component C, this is my component 1, and these are the components and their concentration is given in terms of mole fraction. So some of you may know mole fraction, but those who do not know the mole fraction, what is that? So I'm just right to elaborate this mole fraction. So mole fraction is equal to the number of moles of that component divided by sum of the number of moles which are present in a given system. So suppose here C components are present. So for the component 1, the mole fraction will be is equal to number of moles of the component 1 divided by total number of moles of each component, right? So this is how one can determine the mole fraction. Here n is the number of moles of respective component. Now coming to the alpha phase, we are considering this alpha phase, how these concentration and components are related to each other. So this is my alpha phase, suppose. So this alpha phase is having number of components C1, C2, C3 and so on up to C component. Now coming to their mole fraction. So these concentration terms are related to each other by the relation mole fraction x1 plus x2 plus x3 dash dash up to xc. This is the mole fraction of cth component. And the sum of all these mole fraction of all the components is equal to 1, as you know. This can be understood like this. Consider a mixture of A and its mole fraction is XA and B whose mole fraction is represented by XB. So if I know XA is equal to 0.4, then I can evaluate XB is equal to 1 minus 0.4, that is equal to 0.6. So if I have two components, then one need to be known to me. From there, I can evaluate by applying this formula, the second one. And if you get confused how this sum of all the mole fraction is equal to 1. So suppose we are having two mole fractions, right? So x1 or xa is equal to Na upon Na plus Nb. Xb is equal to Nb upon Na plus Nb. And if you take the LCM of those Na plus Nb, and you will get the numerator as Na plus Nb. So that will be cancelled out and will gives you 1. So guys, you can please solve that in your notebook just to understand this relation, right? If I am having C components, then I need to know C minus 1 component that I am giving you here. This is one equation. For beta phase, we are having this equation again. So this is second equation, and similarly we are having P phases. So this is my pth phase. Then for this phase also I am having this equation, right? So one equation, two equation, and so on up to P equation. So for P phases, we have number of such equations, this type of equations P. Therefore, concentration variables, which I have written earlier for P phases, is equal to Cp. Cp is the total independent variables minus P relations. So this will gives us Pc minus 1. So total number of independent variables is equal to 2 plus Cp, which we have calculated earlier, and now implying the number of relations, so Cp minus P, which I have discussed earlier. You can also do in this manner. That is the alternative method to evaluate the concentration. So here, suppose we are having Tp and concentration variables. So this concentration variables can be evaluated like this. These all things we have discussed earlier. So for alpha phase, we are having this many components and their sum of mole fraction is equal to 1. This thing I have discussed in my previous slide. And if we are calculating the relations, as I told you earlier, so there are C components and sum of the C component is equal to 1. If I come to know C minus 1 less than one component, then one component from this equation I can evaluate. So I am having C components here. So C minus 1 concentration variables must be known to me or are the variables, and the last Cth component can be evaluated by 1 minus mole fraction of rest of the components, right? So here for this alpha phase, we are having C minus 1 concentration variables for this alpha phase. Similarly, for beta phase, we are again having C minus 1. For next phase, we are again having C minus 1. And similarly, for pth phase, we are having C minus 1. If I am having two phases, then 2 into C minus 1. If I am having P phases, then I will have the value P C minus 1, right? So these are the number of concentration variables. So here, by imposing the number of relations altogether, you can calculate the concentration variables. So guys, do not get confused what I have done here. This is just the alternative of this method where we have separately calculated the total concentration variables and total number of relations and we subtracted them. But here I have altogether calculated the concentration variables by implying the restriction, right? In the previous slide, we have done Cp first, then minus P. So we have evaluated the P relations. But here I have made the relationship between the concentration of the component and then 4 number of phases. So altogether I have calculated the concentration variables by implying the restriction. So whichever you feel good, you can do in that way. So if you are following the previous two slides, so you can skip this part, right? So please do not get confused. One more relation is existing in the concentration variables when we are evaluating their chemical potential. For equilibrium state, another thermodynamic requirement is that the chemical potential of a component must be same in every phase. Chemical potential, if you don't know, I will make separate video on the term chemical potential. So it is important you to know that for chemical equilibrium or equilibrium state, chemical potential of each component same in every phase. So here we are having suppose one component, right? Here C1. For this C1, in phase alpha phase, we are having chemical potential mu1. In phase 2 again, we are having the same chemical potential for this component. And in pth phase, we are having the same chemical potential for condition of equilibrium for this component 1. And so for component 1, the chemical potential of this component in alpha phase is equal to chemical potential of this component in beta phase and so on up to. So for this component C1, this many relations exist there. So this equation among the chemical potentials for component 1 in different phases is not considered as one equation. These are the different equations. And this will be considered as chemical potential of component 1 in alpha phase is equal to chemical potential of component 1 in beta phase. Similarly, the chemical potential of component 1 in beta phase is equal to chemical potential of component 1 in gamma phase and so on. So this equation is actually considered like different equations. The reason being writing in this manner is that for such type of equation, no two variables will be sufficient to satisfy all these. Therefore, so rather writing number of different equations, I am just writing this equilibrium chemical potential relation in the form, this will be read in this form, right? Here onwards. So how many relations are there? So there are p minus 1 relations, right? You can see here. Suppose I am having 4 phases, so 1, 2 and 3. Equilibrium relations exist in 4 phases. So 4 minus 1 is equal to 3 equilibrium relations are there, right? So if I am having p phases, then p minus 1 relations in the chemical potential for this component exists between them. So number of relations is equal to p minus 1. For component C, similarly, we are having number of relations is equal to p minus 1. For component C, we are having this many, again p minus 1 relations. So if we are evaluating these for C components, we are having C into p minus 1 number of relations. This is for one component, for two components, and if we all together measure the number of relations for C component in P phases, then for each component we are having P minus 1, and therefore for C components we are having C into P minus 1 number of relations. Now applying these relations in the formula, total number of independent variables 2 plus number of concentration variables. And now imposing the number of relations between the variables at equilibrium condition. So now we are having number of relations P and C minus 1 for these concentration variables, right? So on putting all these values in the formula, number of variables is equal to total number of variables 2 plus Cp minus number of relations minus P minus Cp minus 1. On solving this equation, this Cp will be cancelled out by this Cp, and now we get finally F is equal to 2 minus P plus E. or this is written generally in the form of f is equal to c minus p plus 2. So this is how you can derive this phase rule for the relation between the number of variables with the number of components and number of phases, and you can completely explain a heterogeneous system by knowing all three variables, right? So I hope you understand this, how this derivation of phase rule is done. If you find this video helpful, please like, share and subscribe. Thank you all. Thanks for watching.